Drop a ball on the floor and you can literally watch energy vanish. The ball hits, it makes a little sound, it might get warm if you keep doing it, and it doesn't bounce back to the same height. If you were a reasonable person who has not been trained by physics homework, you'd say, well, the energy is gone. And then a physicist walks in and says something that sounds like a stubborn superstition. The energy didn't go anywhere. It's still here. It's conserved. So who's lying, your eyes or the physicist? Here's what I want to do with you today. I want to teach conservation laws in a way you almost never get in class, not as formulas, not as tricks for solving exam problems, but as a kind of detective method, because conservation laws are not commandments the universe follows. They're clues. They're the footprints left behind when the world has a certain kind of sameness built into it. And once you see them that way, a whole bunch of things you thought were separate suddenly snap together. Energy, momentum, angular momentum. Even why losing energy to friction isn't a violation. Even why rockets can accelerate in empty space without pushing on anything. It all becomes the same story told with different accents. But we have to start in a very particular place, not with an equation, but with a question. Before we conserve anything, we have to agree on what the thing even includes. Imagine you and I are standing in a room with a rubber ball. We drop it from shoulder height. It hits the floor, bounces up, and comes back to maybe half the height. That looks like energy disappearing. Now I ask you, what is the system? Most people, without realizing it, point to the ball. The system is the ball. Okay, let's accept that for a moment. If the system is only the ball, then during the bounce, the floor is not part of the system. The air is not part of the system. The room is not part of the system. The ball interacts with things outside the system. And the moment you allow interaction with the outside world, you have invited the possibility of change in anything you're trying to conserve inside your little box. So the first rule is almost embarrassingly simple. Conservation laws don't say this quantity never changes. They say this quantity doesn't change for an isolated system. That word isolated is doing all the work. Now people hear that and nod and move on. But the way it's usually taught, isolated system is just a condition you check, like a stamp on a passport. And that makes conservation feel arbitrary, like a weird exception rule in a textbook. Instead, treat isolated system as a physical accusation. You're asking, did anything outside our chosen boundary reach in and mess with the books? Now go back to the ball. If our system is only the ball, the floor did something dramatic to it. The ball's bottom deformed, the floor deformed a little, the sound wave went into the air, and there was heating inside the ball and the floor. From the ball's point of view, energy is leaving in all sorts of sneaky ways, as vibrational motion, as sound, as thermal motion. It's not lost in a mystical way. It's simply no longer organized as the up and down motion of the center of mass that you can see easily. So you can fix the violation in two ways. One way is to expand the system, include the ball and the floor and the nearby air. Then the energy that seems to disappear from the ball's bounce is still inside the larger system. It's now random motion of molecules, sound waves traveling, slight deformations. The total stays the same. The other way is to keep the ball as your system, but admit you are not isolated. Then there is no reason energy in that subsystem must remain constant. In fact, conservation laws become useful exactly because they tell you what kind of interaction must have happened if you see a change. That's a very different attitude. Instead of, does energy conserve here, yes or no, you ask, if energy changed in my chosen box, what crossed the boundary? Let's try a simpler example. You're holding a phone. The battery percentage is dropping. You might say, the battery is being used up. That's a natural phrase. But you know it's not literally being used up like fuel in a fire where the material disappears. The phone has processes going on, even when you're not touching it. The energy in the battery is being converted into different forms: light, heat, radio waves, chemical changes elsewhere. If you only track the battery percentage and the screen brightness, you'll think energy vanishes in mysterious ways. But once you widen what you count, heat in the phone body, signals leaving as electromagnetic radiation, the accounting becomes honest. That's what conservation laws are, honest accounting. And now we can say the next uncomfortable thing, the one that people resist because it sounds like it's making physics less real. Here's the uncomfortable fact. Energy isn't a physical goo sloshing around. It's a bookkeeping number that nature refuses to let you change. That sentence sounds like a downgrade, like I'm saying energy is fictional. I'm not. Energy is as real as any quantity we measure in physics because we can predict and verify with it. But it's not a mechanism. It's not the hidden gear inside things that causes motion. It's a number with a remarkable property. When you calculate it correctly for an isolated system, it stays constant through all the changes. If you want to feel how weird and powerful that is, try to imagine discovering it fresh, without being told. You watch all these messy processes, balls bouncing, springs oscillating, chemicals reacting, stars shining, and you find that there's a single numerical ledger that never stops balancing. That's astonishing. And it's not obvious what the correct calculation is. That's why energy comes in different looking pieces. Kinetic energy, potential energy, internal energy, chemical energy, electric and magnetic field energy. Those aren't different species of energy. They're different ways. The same invariant shows up depending on what you're looking at. Now, the common misconception is that energy is a stuff. People talk as if you have a tank of energy inside the ball and it leaks out. That language is tempting because it matches the feeling of losing energy, but it leads to confusion later because you start asking questions like, what is energy made of? Where does it physically sit? Why doesn't it show up under a microscope? The honest answer is, energy is a property of the state of a system, not a substance inside it. When you know the state, you can compute the energy, and that number has this conservation property. Let's make this concrete with something you can picture precisely. Take a mass on a spring, pull it down and release. It oscillates. At the bottom, it's moving fast. At the top, it's moving slowly. Somewhere in between, it's in both. If you only knew about kinetic energy, you would say, at the top, the energy has vanished because the speed is small. But you look at the stretched spring and you realize the spring is storing something. We call it potential energy. It's not magical. It's a way of counting the ability of the spring's stretched configuration to produce motion later. At the bottom, kinetic energy is high and spring potential energy is low. At the top, kinetic is low and potential is high. The sum stays nearly constant if friction is small. That's a clean example of conservation of energy in a system you can almost isolate. Now include friction. And what happens? The oscillations die out. So did energy vanish? No. The mechanical energy, the neat organized exchange between kinetic and potential, has been converted into thermal energy, random microscopic motion in the spring and the air. If you touch the spring after a long time of oscillation, it may be slightly warmer. That warmth is energy, not organized, not useful for making the mass swing in one direction, but energy nonetheless. This is why people think energy is lost. They confuse lost from the form I care about with gone from the universe. Conservation laws are not promises that the thing you like will stay. They are promises that the total accounting will always balance if your system is closed. Now, at this point, many lessons stop and say, great, that's conservation of energy. Let's do problems. But if we stop there, we miss the entire reason the title of this video can be true. Because the way nobody teaches this is not just to say energy is conserved. The deeper teaching is to ask, why does this bookkeeping work at all? Why should the universe allow any such invariant? And to answer that, we need to introduce momentum, not because it's the next chapter, but because it reveals the pattern. Sit on a rolling chair, throw a heavy book, and your body learns momentum conservation faster than your brain does. If you've never done this, you can try it. Sit on something that rolls with low friction, a rolling chair, a skateboard if you're careful, ice skates if you like excitement. Hold a heavy object, then throw it forward. You will roll backward. Nobody has to convince you with an equation. You feel it in your stomach. Now, if you're only thinking in everyday terms, you might ask, why did I move backward? I didn't push on the ground. I didn't kick anything. I just threw something. But you did push on something, the book. You exerted a force on it, and it exerted an equal and opposite force on you. That's Newton's third law. And from that, in an isolated system, momentum is conserved. But again, don't let it become a chant. Treat it as accounting. Before the throw, the total momentum of U plus book is 0. You're both at rest. After the throw, the book has momentum forward. If the total must remain 0, you must have equal momentum backward, so you roll backward. Here's the key. The momentum conservation statement is not about moral fairness. It's about what happens when there is no net external force on your system. The moment an external force acts, the system can gain or lose momentum. That's why, if your chair wheels are sticky and the floor pushes on you with friction, the effect changes. The floor is now part of the interaction, so you're not isolated. Momentum can flow into the earth, which is so massive you barely notice it. So now we have two conservation laws, energy and momentum. And we've learned the first big unifying idea. Conservation depends on what is inside your boundary and what crosses it. But momentum adds a subtle new flavor. Energy comes in many forms and can hide microscopically. Momentum is different. Momentum is directional. It points. And when momentum seems to disappear, it almost always means you've ignored some direction where it went. Let's do a classic misunderstanding. Two ice skaters push off each other. One is heavier than the other. The lighter one flies backward faster. People often say the heavier one gave more momentum to the lighter one. That phrase is dangerous because it suggests momentum is something one person hands to another. But momentum is a property of each object's motion, and the key is that the total momentum of the pair is conserved if you ignore external forces. If they start at rest, total momentum is zero. After push-off, the lighter one has momentum in one direction, the heavier one has equal momentum in the opposite direction, equal in magnitude, not equal in speed. Momentum is mass times velocity, so the heavier one can have the same momentum with a smaller velocity. This is one of those places where conservation gives you a correct statement that your intuition might resist. You might feel that the lighter skater got more because they moved faster, but conservation says the momenta are equal and opposite. Your feeling is about speed, not momentum. So what's momentum really telling you? It's telling you something about space. Specifically, it's telling you that if nothing outside the system pushes it, the center of mass motion doesn't spontaneously change, and this is where we can start sniffing the deeper idea. Why should no external push be the condition? Why not some other condition? Why does nature choose to conserve momentum instead of some random quantity like mass times speed cubed? Here's a way to approach it without mathematics. Imagine you perform an experiment. You set up a collision between two carts on a track. You measure their masses and velocities before and after. You notice momentum is conserved when the track is frictionless. Now imagine you move the entire setup 3 meters to the left and run it again. Does the result change? If the laws of physics do not care where you are in the room, the outcome should be the same. Not approximately the same because the room is symmetric, but fundamentally the same because the underlying rules do not privilege one location. That property, no preferred location, is called space translation symmetry. It's the idea that the rules don't change when you shift everything over. If that's true, you can prove that there is a conserved quantity and that quantity is momentum. We are not going to do the proof in symbols right now, but you can feel why the connection exists. If the rules don't depend on position, then there is nothing special about being here versus there that could create or destroy motion in a particular direction out of nowhere. Momentum becomes the bookkeeping that measures the consequence of spatial uniformity. Now, energy has a parallel story. Ask the analogous question. Run the same experiment today, then run it tomorrow. Do the laws change because it is a different day? If the rules of physics do not care about the absolute time on the calendar, then the dynamics are the same under a shift in time. That property is time translation symmetry. If it holds, there is a conserved quantity. That quantity is energy. This is the moment where conservation stops being a pile of separate rules and becomes a single idea. But before we reveal it fully, we need one more ingredient, angular momentum. Because angular momentum is the one that makes people feel like something supernatural is happening. If you've ever watched someone spin faster just by pulling their arms in, you've met a conservation law that doesn't care about your common sense. Picture an ice skater spinning with arms extended. Ended. They pull their arms in and suddenly they spin faster. It's dramatic. It looks like free energy. They speed up without pushing on anything. So what's going on? Is energy being created? Is angular momentum being created? First, ask the system question. What is inside our boundary, the skater? What external torques are acting? If the skates are on low friction ice and there is no significant external twisting force from the ice, then the skater is approximately isolated with respect to torque about the vertical axis. Angular momentum is the rotational analog of momentum. Linear momentum deals with motion through space. Angular momentum deals with motion around an axis, and its conservation law says if no external torque acts on the system, the total angular momentum stays constant. Now, why does pulling arms in make spin faster? Because angular momentum is not just spin speed. It depends on both the angular velocity and the distribution of mass, the moment of inertia. When you bring mass closer to the axis, you reduce the moment of inertia. To keep angular momentum constant, the angular velocity must increase. This is the same pattern as before. You change one part of the expression, another part compensates so the total stays the same, because the system is isolated from external torque. But you might still object, where did the extra kinetic energy of the faster spin come from? Because the skater's rotational kinetic energy increases when they spin faster. Excellent. That's a real question, not a misconception. The answer is the skater does work pulling their arms in. They use chemical energy in their muscles to move their arms against the effective outward tendency that comes from the rotation. They are not getting energy for free. They are converting internal chemical energy into rotational kinetic energy. Angular momentum is conserved, but energy can be redistributed between internal and rotational forms. So now we have to be careful. Conservation of angular momentum does not automatically mean conservation of rotational kinetic energy for a changing shape, because internal forces can do work. That subtlety is exactly why conservation laws are not the same as nothing changes. Things change constantly. Conservation laws tell you what changes must be compensated by other changes, given certain symmetries and isolation conditions. Now, we've built 3 examples: bouncing ball for energy, chair throw for momentum, skater spin for angular momentum. Each one feels like a separate topic in most classes, but they share a hidden skeleton, and now we can finally say it in the way that once you hear it, you wonder why it wasn't the first thing you were told. Now, for the part nobody tells you, conservation laws are not separate facts. They're what you get when the universe doesn't care about when, where, or which way you run the experiment. That's the core idea, and it has a name. Emmy Noether showed in a precise mathematical way that every continuous symmetry of the laws of physics corresponds to a conservation law. But you don't need to memorize her theorem to use the insight. You can treat it as a practical lens for thinking. Let's unpack it carefully. When I say the universe doesn't care, I don't mean it's emotionally indifferent. I mean that the equations describing how things evolve do not change under certain shifts. Shift in time. Run the same experiment later. If the underlying rules are the same, energy is conserved. Shift in space. Move the whole experiment across the room. If the rules are the same, momentum is conserved. Rotate the experiment. Turn it to face a different direction. If the rules are the same, angular momentum is conserved. Notice what this does. It turns conservation laws into a diagnostic of symmetry. Instead of teaching you conservation laws as separate rules, we can teach you to ask, what symmetries does this situation have? What is the same if I move it, rotate it, or run it later? The symmetries are the deep assumptions. The conservation laws are the consequences. That's a radically different teaching route. It's not formula first, it's structure first. And it makes sense of why conservation laws can appear to fail. Because when a conservation law fails, it's not usually a mysterious violation. It's a sign that either your system isn't isolated or the symmetry you assumed is broken. Let's explore those failure modes, because they're where people get confused and where the new way of thinking becomes most useful. If conservation ever looks wrong, don't panic. Ask which assumption you quietly violated. Start with energy. Why does a sliding block on a table slow down? The kinetic energy decreases. If you only count kinetic energy and gravitational potential energy, it looks like energy is disappearing, but the block and the table are rubbing. Molecules are jiggling. Heat is generated. Sound waves go into the air. The lost energy is in internal degrees of freedom. So energy conservation isn't broken. Your accounting was incomplete. Now momentum. A ball rolling on a rug slows down. Momentum decreases. Did momentum vanish? No. The rug exerts a friction force on the ball, and the ball exerts an equal and opposite friction force on the rug and ultimately the earth. Momentum is transferred to the Earth, which is so massive that its velocity change is imperceptible. The total momentum of ball plus Earth is conserved, but the momentum of the ball alone is not because you've left out the external interaction. Rockets are the classic demonstration that momentum is about systems, not about pushing on air. People say, how can a rocket move in space with nothing to push against? It pushes on its exhaust. The rocket plus exhaust is the system. The exhaust gains momentum backward. The rocket gains momentum forward. The total stays constant if you ignore external forces. No mystery, just careful boundaries. Now, angular momentum. A spinning top slows down and falls. Angular momentum seems to disappear. Where does it go? Into the Earth, through friction at the contact point and through air resistance. The Earth gains the opposite angular momentum, but again, it's too mass. I've for you to notice. In all these cases, the violations are really just momentum or energy flowing into parts you didn't track. Now there's another type of failure, symmetry breaking. Suppose the laws of physics are not the same everywhere because there's a gravitational field. Does momentum conserve? In a local sense, you can still apply momentum conservation with forces accounted for, but the symmetry, no preferred location, is no longer true in the same simple way, because gravity gives a special direction, down. That doesn't mean momentum conservation is destroyed. It means your system is subject to an external force from the gravitational field, unless you include the source of gravity as part of the system and treat the interaction correctly. Similarly, energy conservation relies on time translation symmetry. If the background changes with time, the clean statement of global energy conservation can become subtle. In cosmology, for example, when space itself expands, the question of defining a single global conserved energy for the entire universe is not as straightforward as it is in a fixed background. But even there, physics is not anything goes. There are local conservation laws and precise ways to track energy momentum in general relativity. The point isn't to scare you. The point is to show that conservation laws are not floating commandments. They are anchored to symmetry, and when symmetry becomes complicated, the bookkeeping has to be upgraded. That's intellectual honesty. We don't pretend conservation laws are magically simple everywhere, but we also don't throw them away the moment the situation gets sophisticated. We ask what assumptions still hold and what the right system and ledger are. Now let's stitch everything together in a way that feels like an actual aha, not a slogan. So the real lesson is this: conservation laws aren't rules the universe follows. They're the footprints left behind when the rules of physics stay the same under certain changes. Think about what that means. It means conservation laws are not the deep reason. The deep reason is symmetry, sameness. Conservation laws are what you can calculate and measure because that sameness exists. And it also means conservation laws are astonishingly powerful because symmetry is everywhere. Space is nearly uniform at the scales of your daily life. Time is steady. Rotations don't change the basic laws of mechanics in a room, so you get these robust quantities that refuse to change no matter how messy the process is inside your chosen boundary. This is why conservation laws feel like magic. They let you predict outcomes without knowing every microscopic detail. You don't need to know the exact deformation pattern of a colliding car to know that absent external forces, the total momentum before equals the total momentum after. You don't need to know the exact molecular interactions in a bouncing ball to know energy didn't vanish. It changed form. Conservation laws are like a receipt that tells you the total cost, even if you don't remember exactly what you bought. The categories can shift, snacks can become produce, but if no one added or removed items, if the system is closed, the total is fixed. And now we can answer the original paradox. When you drop the ball and it doesn't bounce back to the same height, energy didn't vanish. It left the form you were watching and entered forms you weren't. Heat, sound, microscopic vibration. Your eyes are not wrong. You watched organized energy turn into disorganized energy. The physicist is not wrong either. They are talking about the total ledger, not the visible line item. So what does this tell us about learning conservation laws? It tells you the usual way, memorizing equations first, is like learning accounting by memorizing the final balance sheet without knowing what a transaction is. A better way is to learn the questions that conservation laws answer. What is my system? What crosses its boundary? What symmetry am I assuming? Are the rules the same if I shift in time, place, or orientation? If a quantity changes, is it because the system is open or because the symmetry is broken? Those questions are portable. You can take them anywhere in physics, and you can use them to avoid the most common trap, treating energy, momentum, and angular momentum as different spells you cast on different problems. They're the same spell in different costumes. Energy is the consequence of the universe not caring about when you start the movie. Momentum is the consequence of the universe not caring where on the stage you put the actors. Angular momentum is the consequence of the universe not caring which way you turn the stage. Now, there's one more twist that's worth saying out loud, because it's where people either become cynical or become genuinely curious. Conservation laws tell you what cannot happen. They don't always tell you what does happen. If I tell you energy is conserved, that doesn't tell you how energy flows. It doesn't tell you how fast. It doesn't tell you what the microscopic pathway is. It tells you that whatever happens, the total number will match at the end if the system is closed. That's not a weakness. That's exactly why conservation laws are so powerful. They're constraints. They let you rule out impossible stories and narrow down the possible ones. And it's also why they can feel unsatisfying if you treat them as explanations. If you ask, why did the ball bounce to half height? Conservation of energy alone doesn't answer. You need details, material properties, deformation, damping. Conservation tells you that if it didn't bounce back, energy must have gone somewhere else. It doesn't tell you the specific mechanism without more physics. Feynman loved this distinction. What is the reason and what is the rule are different questions. Conservation laws give you rules. The mechanisms often require deeper theories, electromagnetism, atomic theory, quantum mechanics. But that's not disappointing. That's the map of physics. Conservation laws are the rigid frame. Mechanisms are the moving parts. So here's how I'd like you to leave this video. The next time someone says energy was lost, you'll have a better question than, where did it go? You'll ask, what ledger did we forget to include? And the absenta. Next time you see a conservation law in a textbook, don't treat it as a formula to plug numbers into. Treat it as a message from the universe about sameness, about what doesn't change when you shift the world in a certain way. Because that's the real reason conservation laws exist. Not because the universe likes balance sheets, but because the universe, at a deep level, has symmetries. It doesn't care about your choice of origin, your choice of clock start, your choice of orientation. And when nature doesn't care, something becomes impossible to change. That's the kind of idea that, once you really get it, doesn't just help you solve problems. It changes how you look at everything from a bouncing ball to a spinning galaxy. And if you want to keep going, there's a delicious question waiting right behind this one. If symmetries create conservation laws, what happens when symmetries are only approximate, or when they're broken? What new behavior becomes possible then? That's where the universe stops being polite and starts being interesting.